Sorry, guys. Yeah. Just a brief summary. So what we talked about is binary search trees. We talked about the classic operations, find, insert, delete, and the new parallel operations, intersect, union, difference. And they basically are parallel versions of these, or like bulk versions of these. And in terms of work and span, these guys are log n work, log n span. And we implemented these using just 3 operations: split, join, and join m. And join m is simply join and singleton, which is a trivial function to construct singleton trees. And for these guys, our bounds are order m plus log m plus n divided by m work, and order log square m plus n span. And intuitively, the reason for this is that you can implement all of these algorithms so that you take the smaller tree and you partition the bigger tree. And when you partition the bigger tree, at the leaf, at the base cases, you get trees of size n over m. Okay, so then your algorithm is basically just an algorithm of this form. At each level, it does work log size of the thing being split, and size of the thing being split is initially here log n, dot, 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 it goes up to log n over m, okay? Because you don't work on these trees individually, you only pay log n over m, and that gives us this log n plus n over m bound, okay? The fact that you only split the bigger one up to a point is what gives you that nice bound, and these are all optimal, right? Okay, good. So we've solved binary search trees, nice, work efficiently, and in parallel. Now the question is, the assumption was that these guys, okay, the assumption was that these operations all require log n work and log n span, right? And then we'll see how to do that now in this lecture. And basically to achieve that, we need balancing. Okay, we need to be able to balance our trees. And as I alluded in the first lecture, there are many ways to do this. In this lecture, we're going to use one way. Many ways. In this lecture, we will use a randomized technique. Okay, good. So I think many of you are not familiar with trees, so let me motivate first what they are, and then we'll go from there. Now suppose that I've given you a set of keys, like 1, 5, 7, 8, maybe 4, I don't know, 9, 3, 11, okay? Now let's insert these into a binary search tree beginning with an empty tree. So initially I have my 4. Okay, next comes my 1. What would I do? Where would I insert 1? To the left, right? Because it's less than 4, so it goes in there. How about 5? That's going to go in here. Okay. How about 7? That's going to go in here. How about 8? That's going to go in here. How about 9? That goes in there. Okay, so I'm not doing any balancing or anything like that right now. How about 3? That's going to go in there. Okay. How about 11? That's going to go in here. Okay. So this ended up being not a very balanced tree. So we got a bit unlucky. Okay. Because of this problem, we do want to somehow rebalance things. Now suppose that I ask you the following question. Let's consider the exact same set of keys, but let's pick a completely random permutation, uniformly random permutation in terms of those insertion orders. Okay? Uniformly random permutation. What do you think that tree would look like? Okay, with of course an expectation, right? It could look terrible, like it could my random permutation could be 1, 4, 5, 1, 3, 4, 5, 7, 8, 9, 11, right? Which will give me just basically just the most unbalanced tree. But the probability that this permutation, if I just pick a uniformly random one, there's only one such permutation. And there's the reverse one, okay? There are like 2 such permutations that are going to give me this horrendously imbalanced tree. What would look like? An average permutation is going to look a little bit like this, right? For 8, I don't know, like 3, 7, right? 9, 1, 11, okay? So let's look at that. Let's look at the tree for that. It's going to be 4, 8, 7, 9, 1, 3, 11. It's actually a really balanced tree. It's almost perfectly balanced. Okay, so between these 2 extremes, if I pick a uniformly random permutation, the tree that I picked, which one will it be close to, do you think? Would it, with probabilities, is it highly likely to look like that, or is it highly likely to look like this? Why do you think? Can somebody give some intuition? Number of permutations is very large. Only a few are on the 2 extremes. Excellent. That's exactly the reason. Can we go a little deeper? Why is it the case that, given that we have so many permutations, why is it the case that the ordered ones are less likely to be? Because there are many orderings like that. So consider this very bad ordering. I could also, this is actually pretty bad too, right? It is another permutation. But somehow, our intuition is correct. Somehow, the tree, if I pick a uniformly random permutation, okay, it's not immediately easy to see, but if I pick a uniformly random permutation, it's closer to this guy than that guy. Any ideas why? Let me help you out a little bit. Suppose I order my keys in a line like this, where this is the smallest and this is the biggest. And let's play a game. Okay, let's take a dart, throw it into the line, onto the line, and let's take that as our first key. And then throw a second dart. Let's take that as our second key. Throw a third dart. Let's take that as our third key. Let's think about the first dart now. Where is it gonna land? Somewhere close to the middle, exactly. Right. So if you got n keys, let's look at this middle that contains 3n/4 keys. So that we've got 1/8 here, 1/8 here, and then all the rest, 3n/4, is in the middle there. Okay, it's with probability 3/4, the dart is going to land here. The nice thing about this, such a thing, is that with probability 3/4, I get a constant factor partition of the keys. Okay, so that is nice because it's basically going to give me a balanced tree. Because I'm going to only, if I get a key here, for example, it's going to be perfectly balanced. If I get a key here, it's going to be reasonably perfectly balanced, and so on. Okay? So if I got unlucky in the first step, suppose my aiming was not good and I aimed here. I got unlucky in the first one. Okay, that happens with probability 8. But then the second one is going to probably land here because this is more likely. And if I can somehow get lucky after every constant number of tries, okay, what's the probability that I'm going to keep hitting these guys? Okay, suppose that I throw my dart 4 times. What's the probability that I'm going to always hit the bad part? It's this. That's very, very unlikely. So after 4 darts, I get a perfectly good partition. Okay? So that means that with very high probability, right? Not very high, but high probability, okay? So after just a few dart throws, I get a very good partition, and I'm good, okay? So that means, for that reason, if we pick a random permutation, chances are that this tree is going to be very balanced. Okay, so that's an interesting observation, okay? So this is the idea behind trees. Basically, this idea was noted. I mean, it goes back to 1980s, right? I think people noticed this idea much earlier than in the early days of computer science. And then the data structure TREEPS was proposed in mid-90s, I believe, late 90s. Oh no, mid-90s. So it's a very nice data structure that actually implements this idea. Basically, what it does is that given a set of keys, it builds a probabilistically determined data structure whose balance is probabilistic and equivalent to a permutation of the keys inserted in this fashion. Okay, question? Yeah.
So you're saying that as the list gets longer, you're sort of multiplying another 1/4 each time the length increases in terms of like the probability of an unbalanced tree.
So are you asking what this is trying to do?
Well, I'm saying, so a dart throw represents like a permute step?
Good, yeah. A throw represents who's going to be the very first key that's going to go into the tree. And we do that by throwing a dart. Okay? So I might get unlucky with probability 4th in my first try.
Right.
Let's not count that. I was unlucky. And I might get unlucky again, and again.
Right.
Now, the fact that I get unlucky 4 times in a row is very low probability, right? But even that is good enough to give me a good balance.
Yeah.
Because after 4 tries, I get a good balance. I got one of these guys. And as soon as I get one of these guys, I get an even partition. The rest of the keys are going to go here, and some other keys are going to go here. And maybe I had a chain of 4 nodes that were like this. But who cares? That's only a factor 4.
So we're squeezing the probability of an unbalanced tree lower and lower by making more attempts? Like
exactly.
More random attempts? Okay.
Exactly. So, you can imagine making more random attempts and let's say that, what's the probability that I'm going to get unlucky 4 times in a row? It's this, it's very low, but eventually I'm going to get lucky. But as soon as I get lucky, I get a very good balance. So I think what I'm trying to say is that achieving order log n balance is very easy because I'm going to get lucky eventually. As soon as I get lucky, I'm done because I partitioned my keys. 3/4 goes here, 1/4 goes there. That is enough to give me a log balance asymptotically. Yeah, so that's the intuition. Yeah, basically, just 50,000 feet level idea is that there are just so many more keys here than the edges. There are more keys in the middle than the edges, and if I'm picking randomly, I'm more likely to pick in the middle, and therefore the permutations are more likely to start with keys in the middle, and so on, okay? And therefore, if I just pick a random permutation and insert the keys in that order, what I get is a balanced tree. Okay, so that's the intuition. Now, what TREEPS does is that takes that intuition and basically builds a data structure out of that. Okay, now my question is, suppose we want to build a data structure out of this intuition. Somehow we want to make it look like it's always a random, it's always a tree that it looks like a tree that you would obtain by randomly inserting keys, okay, in order. How could we do that? Well, the idea turns out to be very simple. What we're going to do is, to each key, we're going to assign a priority, sorry. Okay? And the priority basically going to correspond to position of that key in this insertion order. Okay, so for example, I could give the following priorities to these keys, and then that would correspond to exactly this order. So my tree is going to look the same as as if the keys are inserted in priority order. So these are priorities, these are keys. Okay, if I give the following priorities, let's say that the priorities are 3, 1, 2, 4, 5, 6, 8, 7, okay? Then my tree is going to look like the keys are inserted in the following order. So, okay, 1, 4, 3, 5, 8, 7. Because that's the sorted order that corresponds to these priorities. Okay, if these are the these are the priorities for these keys, my tree is going to look as if I've inserted the keys in this order. And that means, how is that going to look like? It's going to look like 1, 4, 3, 5, 8, 7, 9, 11. Okay, that's how it's going to look like if those were the. Okay. So we imagine these priorities, and we always want to make our tree look like that. So let's now add the priorities in this and then see the structure that we get. Okay, so let's add the priorities. One had the, oh God, what did I do? Did I mess it up? Oh man, what did I? Oh, oh, okay, no, it's fine. It's good. Okay. Did I get it right? Yeah, I did get it right. So this is priority 1. Okay, let's write the priorities, okay? So tell me the priorities for each key. These are the priorities. So 1 has priority 1, 4 has priority 2, priority 3 is 3, priority 4 is 5, priority 5 is 8, priority 6 is 7, priority 8 is 11. Wait, 7 is 9, and then this is 8. Okay, so now what do you observe in this structure? Look at the priorities only of the keys. What can you see in terms of the priorities, the relation of priorities?
They're also a tree.
They're also a tree, as in a binary search tree. No, it's not right.
Any path from the root to the leaf is sorted.
Any path to the root to the leaf is sorted. Excellent. Good. Excellent. Because they correspond to the insertion order. The higher the priority, the later it goes.
I'm sorry, again, just where did we get this, like, random-looking list of priorities?
We pick it randomly.
We pick it, all right.
Magical. So we're trying to pick a random permutation.
Right.
Okay, so the intention, take a step back. The intention is to pick a random permutation. Okay? Now the challenge is that if you had all the keys, you could pick a random permutation. But in binary search trees, trees are coming one by one, for example. You can't pick a random permutation. You don't know what the future keys are going to look like. So that's what we want to simulate. How are we going to do that? We're going to give priorities. Priorities are random. And we're going to pretend that priorities are the permutation, basically. That's what we're trying to do. Priorities give me the sorted order. Priorities give me the permutation for the keys. Okay? So it's an online way of permuting the data as it comes. When the new piece of data comes, I say, I'm going to pick a random priority and give it to it. Basically means that it may be inserted in the past. As if. Okay, so now this path to root to leaf, it's a sorted order for any one of them. What exactly, let's minimize that requirement. The minimal requirement that basically guarantees the same thing is that if you look at any node in the tree and look at its children, the children have smaller priorities, right? Because that's just by construction, right? 4 has smaller than 5, 5 is smaller than 7, 6. They're not exactly 3 ordered, because, for example, 6 is greater than 5, but it's on the left. but they are ordered in the sense that, in this sense, a node has higher priority, lower priority than its children. And you know a data structure that actually does that exactly. What is it called? A heap. Okay, so it's heap ordered. So the priorities are heap ordered. And what are the keys ordered? Tree ordered. Keys are tree ordered. And what do we call this data structure? Tree heap. Hence the name treep. So that's where that name comes from. Okay? Okay, so reflect on that a little bit. Any questions? Okay. So let's get down to the details then. Okay, let's see how we can actually implement such a thing. Let me just quickly look at my notes for consistency. Okay, good. So what I'm going to do is I'm going to write the type for it. Data type. Okay, alpha tree is tree yip, you can think of it as. So it's a node of left subtree times key. Okay, key is alpha times int. This is priority times alpha tree. Okay, so what we have is basically, instead of key just storing a single key, we also store a priority in our tree. Or we have a leaf, right? Just standard, either that, or we have a leaf, which is empty. And the invariant is that when we have such a thing, the invariant is going to be that the children of a node u, v, root, the priority of the root is less than the priority of its children. This is the key invariant that we want to maintain in our data structure. And the theorem is that if these priorities are picked uniformly randomly, and if we maintain this, the tree is always going to be probabilistically balanced. The tree height is going to be order log n with high probability. Okay, I won't prove that, but I gave you the intuition for why. It's basically the fact that when you're picking random priorities, it's highly unlikely for the tree to be unbalanced because you're more likely to pick trees that actually divide the space in the middle. Okay, that's it. So now, how do we, just as an exercise, let's write the singleton function. Singleton, what we're trying to do is make a tree out of a single key. What we're going to do is let P be random. Okay, we pick a random priority. And then we're going to return node. Okay, leaf. Key, priority, comma, leaf. Okay, that's our singleton tree. Sorry? It matters a little bit, yeah. You want them to be, for the theory to work out, you want them to be unique. Each key to have a unique priority. So if you pick it to be very narrow, like if you're picking binary priorities 0 and 1, this won't work because pretty much a bunch of keys are going to have 0 priority, and a bunch of them are going to have 1 priority, and you can't tell the difference anymore. So it should be at least, a couple of times n being the number of things that you want to store in there. So a fair bit of randomness will be involved. So typically it's an integer word. So it typically is 64 bits in a typical implementation. So plenty of randomness. Exactly. You could still get. Not really. No, it won't break or anything. If you have collisions, it won't break the data structure, but the bounds are going to be a bit off. But small factors. Yeah. These are good questions. So what happens if your probabilities collide? It won't break your data structure. It's just your bounds are going to be a little bit off, right? Okay, that's a singleton. Okay, so let's implement. All we need is split and join, remember? Okay. So find split given a tree, split with a key. So let's draw a heap. Did we have one? Okay, let's draw one so that we can actually look at it and then think about it as we. Is it okay if I erase this? Is it okay? Okay, so let's use our same keys, maybe something like this. 4, 1, 3, 8, 7, 9, 11. And let's suppose that we have, we can't even think of priorities as being gone because the order really tells us what the order of the priorities are, and we don't really need to know the absolute numbers. Okay. So remember, what we want to do is split this into 2 trees such that based on the key, the left is going to be containing the stuff that's less, the right is going to be containing the stuff that's greater. So if, for example, key is 5, okay, here is what we want to do. We want to say 4, 1, 3, the left, and we want to say 8, 7, 9, 11 is the right. So the trees, those are the results. Okay, split at 5. Note that we preserved the relative order of all the keys. That is, we did not shuffle them unnecessarily. It's not needed because they are priority ordered already, so there's no need to shuffle them around. So we're just going to keep them exactly the same. If we split at 8, or let's say split at 7. If we split at 7, we're going to get something like 4, 1, 3, 8, and then 9, 11. Okay, this is key 7. Wait, did I miss something? I did something funny, but that's not right. Let me do 8. Sorry. So it's 8, 7. That's there's something interesting happened here. If we split at 8, right, 7 is going to need to go into this tree. Where should it go? It should go right under 4 because its priority is greater than 4 in this subtree, so it's going to go right under 4. It should be clear, convince yourself of this. If I give you the priorities for the keys, there is exactly one tree corresponding to those priorities. Assuming that the priorities are unique, there is exactly one key that corresponds to those priorities. And you construct that tree by sorting according to the priorities and inserting the keys one by one according to that sorted order. Okay, so let's write our split function. Any questions? I know this is it's It's not easy stuff, huh? You have to reflect on it. But I'm sure it'll help everybody. Good, so those are two examples. Let's try to write the code for it. So if my tree is empty, there's nothing to do, right? I'm just going to return not found, which is false, and then leave and leave for the left and right subtrees. If, however, it's a node consisting of a left key priority pair, let's call this, maybe use a different letter for keys we'll use KK and priority. And we have a right subtree. Now we're going to split. Okay, what do? Well, we have to figure out which direction we're going to go, right? So we come in here, we have our key. We're going to this guy is going to be either on the left side or the right side. How do we know? We compare the key to this guy, okay? So this is our KK, the root. If key is greater than KK, we know that KK and all its left subtree is going to go to the left. Okay? So we're going to basically continue to the right-hand side. So we have to compare. So let's do our comparison. If K is less than KK, then. Okay, so then we're going to basically, if K is less than KK, we're in this region here. What we know is that whatever is in here is going to be greater than KK and it's going to be on the right-hand side. So we don't have to worry about that. So what do we do here? Suppose that we do a recursive call and we split that into L and R. Okay, imagine that situation. Suppose we come in here and then we know that the split is going to have to happen on this side. So we take the left subtree and then split it into two trees, L and R. Now somehow I need to take those and then combine with this guy that I didn't touch and return a tree. How can I do that? I know that my key is in between, right? Everything on the left is less than the key. Everything on the right is greater than the key. So all I need to do is take this R and hook it up here. And that's what I return, basically. Okay, so that's basically the implementation. If K is less than KK, then what we're going to do is we're going to do a recursive split. Let's call this LL, found RR. Okay, so call this LL less than key less than RR. Which one was found first? Okay. Found LLRR is going to be split because I'm less than because the key is less than the key, I'm going to split the left subtree. So split the left subtree with L. Oh, I'm reversing everything. So TK, LK. It's bad. As long as it's consistent, it's okay. So we're going to split the left subtree, and that's going to give us LL and RR. And then it is very simple. All we need to do now is we know that R and RR are bigger than the key. And furthermore, because everything in RR was less than, the priority was less than this guy, all I need to do is just hook it up there. So I'm going to return, my result is going to be found, LL. And for the right side, I need to put these two guys together. And I do that by creating a node with left side RR, the priority that I have, KKP, and R. That's it. And that's what I return. Okay, let me explain it once more using the example. Maybe we'll use an abstract example. Sometimes abstraction is good. So we have KK here, okay, and we have R here and L. I come in with a key that is K. Now, there are two cases. K is either greater than this guy or equal to that guy. I guess there's a third case where it could be exactly the same. Let's handle that later. So let's say that that's a simple case. So let's say it's less than KK. So we're going to go down here. If it's less than KK, what I know is that this stuff here is going to be on the right-hand side of my return. But this stuff here, it contains keys that are both greater than and less than KK. So I'm going to split this. So I split this into LL and RR. And what I know, by definition, is that induction is that this holds. All the keys in LL is less than K, and all the keys in RR are greater than K. Good. Ultimately, what I want to return is a set of trees that contain all the keys greater than R and all the keys less than R. So this, I'm done. I don't have to do anything. Those are the keys that are less than K. Now for the keys that are greater than RR, all I have to do is hook this up to here, because the priority of this guy is greater than all the priorities on the left subtree. So I just need to hook it up. Okay? So let's write the easy case. So let's make this else if K is equal to KK, then we return true. And what do we say? We just return these guys, right? L and R. If it's equal, we're done. We just return L and R. Yeah.
So two things. One, we're also doing the symmetric case. We have to kind of sort of copy the symmetric case for K greater than K. Right?
Good. So exercise, pair up.
Yeah.
Finish up the symmetric case.
Right.
Yeah. Finish it up with your friends.
The question I had is, we're just carrying around P. I mean, we're not using it. It's just sort of like dead weight.
Pretty much. The only reason that you need it is in order to reconstruct this node again. In order to reconstruct the tree, I need to make a tree, right? So how do I make a tree? I have the right in my hand, I have RR, and I need the priority and all that.
So split on BST and split on tree is like really not different at all, because the added structure from the tree contributes nothing to the split.
No, in this split there's really nothing going on. Yeah, so that's a good observation. There's nothing interesting that we do with priorities. In the join, we're going to need to deal with the priority, but in this, we don't need to do anything. We don't do anything with the priorities. That's an excellent observation, yeah. Okay, pair up with your friends and finish the symmetric side. Quickly, yeah. Let's split the other part. Let found LL, RRB split RK. So we split the other side. And now what we know is that RR is all the keys that are greater than K. Now for the left-hand side, we have those on the left and LL. So we need to return in found node L, KK, LL, and then R. Okay, did you all get that? Yeah, very good. So that's it. So that's pretty much it. Right? Good. So that's split. And as your friend observed, we don't do anything with the priorities because the tree is already structured with the priorities, so we don't have to do anything. RR, thank you. Yeah. That's right, thank you. Good, so let's do the join, okay? Now in join, we're going to do some priority shuffling around. So what do we have in join? We have two trees. Okay, so let me use this for example. Now here we need to know the priorities, okay? So, let's actually use, let's say that I have two trees, 4, 2, 3, 5, and then here I have like, let's say, remember in join, we have to have the invariant that all the keys on one tree are less than all the keys on the other tree. So I'm going to use letters for succinctness. So let's say we have, D, B, A, C. And you assume that all the letters are greater than all the numbers. Okay, that's our assumption. And then let's say E here. And internally they are ordered. So suppose we're given these two. So now we need to join them. Okay, it's not type safe, right? But assume that those are numbers. Okay, just cross your eyes. But these are stand-in variables for numbers. Okay. Well, I guess I should just, why am I making things complicated? It's complicated enough. Just use numbers. All I need is 7. No, I can't have 5. 6, 9, 8. Okay? Suppose that I have this. So the invariant holds. Everything on the left is less than everything on the right. Now, we're going to join them. And recall that they have priorities. Right? So this guy might have priority. Maybe we can use letters for priorities. So that would be easy. That would make it cleaner. Good. So let's use letters for priorities. This guy has priority A. This guy has priority, let's see, E. This guy has G. This guy has I. Okay? And let's say that this guy has priority. Okay, I don't know. Tell me some C. L. Okay. This. B. Okay, that would.
Higher than C.
It's going to have to be higher than C. Yeah.
We need to keep invariant. So let's use H.
H. Okay. This.
X.
X. Okay, so those are our priorities. Now, what we want is construct a tree that contains both of them. Okay. And we know that tree is unique. Because given the priorities, it's going to have to be unique. And we can determine the shape of the tree, actually, by sorting the keys according to their priorities. Let's do that. So initially, the first guy is 4. The second guy is it 7? Is that right? We don't have B. Do we have D? No. And then 5. F, G is 2. H is 6. And go on. Is it 3? 3, 9, and X. 8. Right? Okay, these are according to the priority sort. So we get like, A, C, E, G, H. 3 is what? I. 9 is L, and 8 is, where is it? X. Okay, that's our sort. So now the tree that we expect is basically inserting them in that order. So we expect 4, 7, 5, 2, 6, 3, 9, and 8. Okay, that's the tree that we expect. Yeah?
So, priorities are bound to the keys?
Yes, they're paired.
Different keys, so, the priorities would be same for both the keys?
Let's assume not. they could, like, in a real implementation, you can get collisions, but let's assume not for our purposes, yeah, for analysis, yeah. Okay, that's the tree that we want, determined by the priority. So now that's what we want to construct from these two trees. How can we do that? Okay, we have some nice locality properties, right? We know that everything, we don't have to compare or sort anything like that. We know everything in here has the local heap property, and everything in here has the local heap property. By looking at these two, can I determine who's going to be the root, for example? The lowest one, right? And it can't be any one of these guys because those are the lowest ones. So I just need to compare these two. So I compare them, and then which one is it? 4, right? So we get the 4. Now, okay, good. We get to 4. So now how can we proceed? What can I say about the left subtree of 4 in the result tree? It's going to have to be this guy over here. Okay? So this guy over here, I can just zoom, take it. Why? Because, well, we know that everything in here is greater than here already. And this stuff here is already less than that. So that's just going to be on this side. Okay? How about, what am I going to do on the right-hand side? It's a bit more complicated, right? Can I recur? I think I can, because I've already determined the root. I have my right-hand side. And that needs to be joined with, this is all that I have. I just need to recursively join that with that. Okay? That's it. No, that's the algorithm. So I just recur. And then when I recur, what happens? Okay, let's continue just for fun. Okay, we're going to get C, because that is the lowest priority. And 7. So we're going to immediately take, we're going to take the right-hand side of that, because it's coming from the right tree. So we're going to take 9, 8, exactly as this. Okay. And then we're going to recur into 5 and 6. When we hit 5 and 6, E and H, we get 5. And then 6 is going to go to the right recursively. Okay. So that's done. Okay, let's write the code. Okay, fine. Join. What did we call these? Our trees, U and V's, or something like that? Yeah. No, T's and U's, right? T and U. Okay. So we do some case analysis. Case T comma U of, if T is empty, then we know that we return U. If U is empty, then we return T. Otherwise, we've got 2 non-empty keys, so we're going to have to compare the keys. So we have node, let's say LT, comma, KT, comma, PT, comma, RT, comma, okay, again, node, I have LU, comma, KU, comma, PU, comma, RU. Okay, I split my things. So now I'm going to compare the priorities, because it's priority ordered. So let's consider the case if PT is less than PU. In this case, what I know is this guy is going to become the root. So, and furthermore, I'm going to have to now reason about the fact that this is going to be the root. The left, it's coming from the left subtree, and its left subtree is going to be smaller than everything in here, so I can completely keep it. So now node, what I'm going to return is LT, and the same, KT, comma PT. And for the right, I'm just going to join, right? Join RT with U, basically. That's that. Otherwise, it's the other way around. So this guy, in that case, has the lowest priority. So that's going to become the root. And I can do the same reasoning for its right subtree. We know that it's greater than that, and we know that's greater than that. So it's just going to be exactly the same. And on the left, I'm going to join. So I'm going to join on the left T, comma, RU. And then keep the priorities exactly the same. K, U, comma, P, U. And then R, U. Oh no, I messed up. Join T, comma, LU, and then RU. Okay. That covers it, I think. And that's the join function. Now what's interesting is, taking a step back, what's interesting is that all of the, as your friend noticed, Quinn noticed, all of the binary search tree specific, balancing specific operations are happening in join. In the split, we didn't do any of it. Okay? So now I'm going to go to the split, and then I'm going to do a little change in that piece of code. A tiny, tiny change. So recall that in the split, what we did was we kept one of the trees the same and split the other one and then joined this with that. Okay, joined two of the trees. Where did that happen? It actually happened here. This node is actually a join M, right? And this node here is a join M. Okay? So let me replace in the code there this with join M. Okay, whatever, right? Join M and join M. Where join M is defined as make a singleton and do double joins, okay? So with that change, let's say that you want to apply the same technique to a different binary search tree data structure, splay trees or whatever your favorite one, AVL trees, red, black trees, whatever. The only thing that you have to implement is the join function, which implements the balancing criteria for that specific data structure. Everything else, the code remains exactly the same, including that of split. Okay? It turns out none of the data structures existing that are known to us make any other balancing operations other than in that one isolated function. And everything else can be implemented in terms of that. So join is the only one where data structural specific things are happening. The rest is template, exactly the same code. Okay, good. So now, what's the working span of these guys? These are sequential functions. They're just going through branches. Right? They're basically following a branch, each one of them, and doing constant operations along the path. This guy's just following a branch, constructing some nodes. This guy's following a branch, constructing some nodes. Just follow a branch down to a leaf. Okay, they're all assuming balance. They're all log work and log span. Okay, so mission accomplished. Remember, our assumption was, which I erased here, was that all we needed to get to optimal bounds was a log n, working span, split and join. And we showed that that's doable, so we're done. Okay, and this works for many other data structures. Okay, questions?
When you
No, they don't.
Okay, then we need to consider a third case in this case. We have only one k less than k.
Yeah. So this is the one. Sorry, I added that later. Yeah, sorry. Yeah, you're right. I added that. I sneakily added that when you weren't looking. I was trying to trick you there. Mission accomplished. Okay, so when you were looking, I just inserted there. You're right. So that's important. That's there. Yeah.
Does anything change if we allow duplicate elements in any of these structures? Like, because if you're going to sort a list that has duplicate elements, and you could put it into this tree and work back out, but maybe you want to preserve duplicate.
That's a good question. I don't think anything will change. I don't. Typically, in these data structures, you don't allow duplicates. That's usually an assumption. But I don't see any. Yeah, like you'll have like union is going to have to, right? You're going to have to. There is not a fundamental problem, but you're going to have to change your data structures. Like union, delete. What does deleting a key mean? Do you mean delete a single instance of it, multiple instances of it? All of these now come into question. So now, these are typically used for sets and dictionaries, right? So it should be clear that what we've done here is completely sets. Everything is unique, keys. Dictionaries are simply key value mappings, right? Everything here trivially generalizes to dictionaries. All you have to do is change your type to carry a value around. Everything else is exactly the same. Not a single line of code will change. Okay, all you have to do is add a value to your type definition. Now, what you're saying are called sometimes bags or multisets. Okay? And I believe these data structures can be adapted to support multisets, but you have to think a little bit about them and make some small changes. But I don't see a fundamental problem. That'll be okay. Yeah. Bags and multisets are sets with duplication, basically, with duplicates allowed. Okay. Good question, yeah. More questions? Yeah. Okay, yeah. It could be wrong. I have to look at my notes. Go on. We'll find out. Oh my God, I reversed the priorities. Okay. Yeah, go ahead. I'm joking. Yeah. Seems like I.
Why is it okay to put LT in the result?
Oh, that one right there. So this, yeah, we do the same thing on LT. That's a good question. Yeah. So let's think about that. Yeah, it's a very good question. So, good. So let's abstract our trees, right? So we have. Let me use that part of the board. I think that's going to be nicer. So, where's the eraser? It's basically the assumption. The reason is that we make the assumption in join that the left argument, the first argument, all the keys in there is less than all the keys in the second one. So therefore we know that that's going to be the same. So let me show you what I mean by that. So we have T, okay, we have LT and RT, and we have U, LU, and RU. Okay, so in this case, we know that the priority of T is less than priority of U. So T is going to go to the root. Okay? So we did that. Now, let's think about what the left subtree of T is going to have. We know that everything in LT is going to be in here. Okay? Is there anything else?
There might be some things from you.
No. Because we have this assumption that all the keys in here is less than all the keys in here.
I thought we were comparing priority.
Correct.
Oh, shoot. Okay.
Yeah.
All right, thank you.
Yeah, no problem. Yeah.
You know,
Yeah. And
that's what the saving comes. That's the beauty
Yeah,
of the
that's-
probabilistic thing. Is that
Yeah.
in every iteration, 1/4, because there are two subtrees, and there is the right of the left,
Yeah.
the right of the right. Match.
Exactly,
It just
that's exactly right. That's exactly right. Yeah. So you are taking advantage of the fact that this is less than that, and therefore, yeah.
the surprise is we don't get perfectly balanced back.
Yeah. Exactly. Yeah. Exactly. But it turns out, even using other balance criteria, you can implement join. Other balance criteria as well. It's not hard. The reason is that, suppose that you were using some other thing, red-black tree, right? Well, the same thing is going to be happen here. This guy is perfectly balanced by itself. You don't need to do anything because you're keeping its root as well. The invariants remain exactly the same. You might have to do something on this side, but you're recurring into that anyway. So, pretty much, yeah. I mean, unless you are, I'm sure there are cases where you have to do something, but in many cases you don't. Yeah. Okay. Good. These are good questions. So I know this is a lot of intellectual, like stuff in the head. So I'll give you two choices. We can either stop here so you have some energy to listen to Gabby in the afternoon, or I can tell you a little bit more about how to augment these things with additional properties that's called augmentation. So you can do fancier things with these things. It's up to you. What do you want to do? Are you cooked already?
Let's do augmentation.
Let's do augmentation. Are you serious?
Yeah.
Oh man. That was unexpected. Okay. Okay, let's do augmentation. Okay. Okay, so yeah, in many cases, in addition to these keys and values in your tree, you want to keep certain information about your subtrees. Okay, so let's say that you have a tree like this, and then you have key value pairs like this. Key maps to, Joe. 2 maps to. These are the social security numbers of these people, for example. 2 maps to Alice. 3 maps to. In each one of these nodes, you can have this information. And being this binary search tree, this thing is effectively sorted according to the social security number. 3 maps to, I don't know, X, etc. Now, let's say that the nice thing about binary search tree is that it allows you to do lookups on the key, which is in this case the social security number. But you might also be interested in things like, give me the 5th person. Okay, give me the 7th person. Give me the 8th person. For example, if you're implementing sequences with binary search trees, one of the key operations on a sequence is give me the nth person, nth in the position, the thing at the ith position, right? So you want to be able to index into this and then find, for example, this person would be she would be 1, okay, I don't know, I can't count. 1, this is 2, right? 3, 4, 5, the 5th person. Okay, so when you talk about the 5th person, this is where you want to come to. Now, these types of operations are not inherently supported by binary search trees, but they are not hard to. It's not hard to augment the data that you keep at the node to support such operations. Okay, and there are many, many variants of this, right? You can. This is one example. Another example could be maybe the data here is the names. That's not a very good one. But let's say that the data is something else. Okay, so this is the social security number, and let's say that this is the salary of the person in your database, and you want to know the max, min, etc. You can keep that data by augmenting these nodes and keeping at each subtree the max salary or the min salary and so on. So you can keep these types of information at the root of the subtree, so that the idea would be when you're computing interesting queries, you don't have to descend into that subtree and look at everything. You just look at the root, and the root kind of summarizes the information that you're looking for. Okay, so many applications of this. This is called augmentation, and basically the basic principle is that all of these are possible, really easy to do, because if you look at our split and join data structures, all that they are doing is putting together trees into nodes. The only operation that we do in all of these split and join is the only interesting thing that we do is, we take a node and take a left subtree and a right subtree, and then put a key, and new priority or whatever. Basically, we're just joining things up, but at the node level. So the fundamental primitive operation is I'm given some tree, L and R, and I'm given some key, and I put them together into a node. Now, suppose that you augmented your trees so that the value that you are alpha L, alpha R are at the root of the trees. And suppose that they are consistent. The only thing that you have to do is compute the value at the root. And if you're a little bit careful about your operation, all you have to do is typically, run some function on this and on that. Okay? So based on this intuition, you can change all of your code to carry around this augmentation function f, which can again be parametric. It can be set, at the top level by your functor, whatever, so that it doesn't care about, it's not specific to the function. It's just as long as the function is able to compute the value for the node from those of the subtrees, you're good. Example, suppose you're trying to keep the max salary. So this would be the max salary of this subtree. This would be the max salary of this subtree. Your function f would be just the max. So you're done. Okay? If you want to support indices, indexed lookup, like suppose that you want to implement sequences with binary search trees, what you want to be able to do is find a particular element, the nth person, ith person. How do you do that? Okay? That's actually hard to do, right, if you don't augment. Because you have to basically do some kind of traversal, and it'll take you linear time. But with a simple augmentation, it's actually very easy to do in log work and span. And what would that be, simple augmentation? Suppose that for each subtree, I keep the size of that subtree. Suppose, for example, that in this example, I keep how many nodes there are in a particular subtree. So this subtree would have 3, this subtree would have 5, this would be 1, this would be 1, 1, 3, and this is 9, I believe. Right? So those are the number of nodes in each subtree, including the root. Suppose now that I'm searching for the person in position 6. Okay. What can I do? I can come in here. I'm looking for 6. This guy has 9 things in it. This guy has, sorry, I have to look up this guy. This guy has 5 things in it. Okay. Therefore, what I'm looking for is in here. So I just go here. And then I say 6 minus 5. I'm looking for the first thing. Okay? So when I come in here, I look at the right subtree. There's nothing on the left. It's 3 things. It must be on this side. So I go down here. And then I find this vertex. Okay? So basically, if I augment my subtrees with these number of vertices, then I can find, this is called a rank query, ith element in the sorted order of keys in log n work. Because I know how many things are in each subtree, and then whoop, I can swoop in and get the right thing. Okay? I can also find, sorry, this is actually called a select query. Okay? A rank query is something like, this says, given a key, find the number of keys that are less than it. In other words, the position in the sorted order. Okay? So then, in that case, I come in and do a similar thing. I now look at the key, now compare the keys. If it's greater, I'm going to go in there. Now, because it's greater, I know everything in here is greater than that key. So its rank becomes 5 plus whatever, and so on. So I do a little search, and as I do the search, I search for the key basically, and that's going to carve out a path. And I just take the subtree sizes from the paths hanging off, add them up. That's the rank of a given key, because that key, the path, basically identifies uniquely all the subtrees that contain keys that are less than the key, and I just sum them up. And then again, log n work and log n span, I'm able to figure out the rank of a key very efficiently. And to maintain this, what I do, suppose that I want to maintain, what I want to do is subtree sizes. I come into my data structure and throw in an int here. That corresponds to the subtree size. And I update my node functions so that every time I construct a node like this, I add in the subtree size. I say, okay, the subtree size is size of LT plus size of this thing plus 1. Okay? As simple as that. So a simpler way of doing that is you turn all of your node functions into a function that's called, let's say, make node, and the make node does the right thing for you, and you're done. In constant overhead, space and time overhead, you can do this augmentation. Okay? Sorry, I'm going very quickly because we don't have that much time. But the details are, again, like including full implementation is in the notes. So you can look over that. Okay, questions? Yeah. Big O notation, what?
With several varieties. Not here, but previously.
Yeah.
What does that mean?
What does that mean? It means, let's say that we have 2 trees, right? I think we had 2 trees. When we say something like this means it's asymptotic and asymptotically proportional to the size of the first tree plus the size of the second tree. Yeah.
I guess what is the exact statement of this one?
Big O of m plus n, any function. It could be any function, right? So yeah. So asymptotic notation is a functional notation. It's for any function of any number of arguments, fixed number of arguments, you can generalize that. So it basically means asymptotically the function, right? So you would, if it's 2 variables, right, you would have to find If it's in the 2 dimensions, you basically say, except for a fraction of the space, whatever you're trying to establish holds. That's all that asymptotic notation says. So if it's 2 variables, you just have 2 constants beyond which your theorem's hold. No, no dependencies. Okay, that's a good question. So that would be no, that you wouldn't have to have any dependencies, I don't think, yeah. Okay, questions? Okay, we'll see you in the afternoon. Have a good break.